All right. Okay, so I'm the last talk before we go off on a break, so I'm going to talk for a few hours. So yeah, I wanted to talk about what comes after every one of you here has done the hard work of actually finding a candidate, and you want to let someone like me, a theorist, try to work out what's going on, or at least give you some answer, which is most likely wrong. So there's no need to tell this audience that, the rate of transients is exploding. We're getting so many transient observations, and this is going to keep rising in the near future. But really what we want to work out, what the science goal in the end is to try and understand what the light curve or spectrum or et cetera is telling us. So I'm sure many of you have seen this plot at the bottom, which is just showing you the 1708-17 kilonova. You can fit those observations and you can try to ultimately work out, all right, this is how much ejector mass this merger had. This is what, the properties of that ejector mass were, et cetera, et cetera. The way I go about this is through the guidance of Reverend Bayes. So if you're not a Bayesian person, you can have a fight with me afterwards. So really what the goal of this project, this Redback package that I've been developing alongside many other people for a long time, is to have an open source modular tool that you can, not just me, but many other people in the community can come in. If they have a model, they can put that model in. If they have a different type of observation, they can put that observation in. And through Bayesian inference, try to understand what the observation is telling you. And the key goal is that it has to be adaptable. So it has to be something that a user can pick up and within a few lines of code fit their favorite transient. But then it can actually extend all the way to the powerful workflow that someone who's an expert in this sort of analysis technique would try to do. Also has to be end-to-end. So you want to be able to validate whether the whole package is working properly, whether the whole infrastructure is working properly. So you want to go all the way from simulating as realistic as observations as you can, all the way to actually fitting, all the way to the science that you want to interpret. And you want to see if it's all validated correctly. So when the real thing happens, you can be sure that it's right. And then also what's becoming increasingly common is that we're getting these joint observations. So obviously the gravitational wave observations have been rare, but historically we've been regularly observing a supernova or some other transient, and that always comes with a light curve, but then usually also comes with a spectrum. And so you want to jointly model both things to try and understand what's going on. Similarly, we've now regularly started seeing these GRBs, which have got an additional component on top of them, such as a supernova or a kilonova. Now you want to model both of those things together to again interpret what's going on. So this is how this whole package is structured. And so Monica already mentioned Bilby, which is a key part of the ecosystem. So I was also responsible for building Bilby and doing all of that. So it's all sort of works the same way exactly. So if you're familiar with Bilby, you're already sort of really familiar with how Redback works. But there's all these different sort of objects that are handling, and you stitch together all these different objects to make your different workflows. So for example, there's a simulation module. But if you don't like how that simulation module is stitched up together, how that's coded up, you replace that entirely with your own module. Similarly, there's APIs to get data from different satellites, which I'll show in just a second. But if you don't like how that API is set up, you get your own. And it's just at the end of the day, it's just a CSV file that you're getting all the data in, so you just do it that way. Similarly with models, there's a whole bunch of models already implemented, but at the end of the day, they're just a Python wrapped function. So if you don't like a model, you replace the model. And then the likelihood and prior are again, analytical functions of some sort. The samplers, the way you actually sample something, actually get a posterior out in the end is through this package Bilby. And so there's about 15 or 16 different samplers, open source off-the-shelf samplers that are already implemented in that package. And so you just replace them and then in the end, you get this, light curve or posterior corner plot, and that's how you want to interpret your observations. So as I said, the workflows basically come together as different parts of the pipeline sort of stitched together to make 3 different workflows primarily. So you can get data from whatever satellite you want. You create this transient object, which is just doing some processing and storing it all together. You specify a model. You set a prior, which is just describing for every model parameter what are the range of parameter values I would be allowing, etc. You specify a sampler, and then you fit. You can also go the other way. You can, instead of just choosing, instead of actually fitting an observation, you can go choose a model, draw randomly from that prior, let's say 1,000 different parameters, and say what would that look like in Rubin? What would that look like in Swift? What would that look in Argus Array, et cetera, et cetera. And then you can go even a step further. For every single one of those simulated observations, if I try to fit something, what would I actually recover? What would I infer from those simulated observations? And that way you can go about checking for your survey strategies, or what the projected constraints from future surveys will be, and so on. And so, for example, this is how the interface works for getting data. So, for example, if you want to get the data from Think, which is a broker, you have one line of code which says this is the name of the transient you want, which is some ZTF name, I don't even know. And then you know it's a type of supernova because Swift has done that, Think has done that hard work of classifying, or someone else. And you would then get a data file at the end, which is just a CSV data file. Lasserre, you can do the same thing. Open Access Catalog, which was this amazing catalog put together by James Gulichin et al. And now that catalog is dead, but you can still access it through this API. So all that data is still there. And you can get basically that entire data, for example, for this tidal disruption event. I don't know if people actually ever use BATSI anymore, but you can still get data from BATSI. And then Phil is going to love this. You can get data from Swift through the burst analyzer, but it secretly opens a web page in a headless browser.
It doesn't use our API together.
No, it doesn't use the API. So yeah, you're going to love that. So we're going to eventually replace it to the API, but yeah, I didn't even know the API existed until I met Jimmy and Hellwire. So the data is just saved as a text file, and it's just a pandas data frame, so you can inspect it and so on and so forth. But where the magic happens is that you can load that data into this transient object, which is going to try and look for other things from the metadata that it can, for things such as what the location of the transient is, what the redshift is, if the redshift is from a spectrum, and things like that and so forth. But of course, if you have your own data, such as, for example, it's just a text file that you have loaded up, you can create your own transient object, and then you can do fitting on that and various other things. So there's sort of 6 different transient objects. So they're basically, essentially, they're processing everything together, but they're written in specific ways for different types of objects. So an afterglow is, by definition, almost always going to be non-thermal. So it has different functionality, whereas a supernova is, again, something else. Tidal disruption is something else, and so on and so forth. And so if you don't know what something is, there's a generic transient class, which is just written as generically as possible. And then if you know if it is an optical transient, there's something for an optical transient. But these are sort of the 6 different main classes, and these are the type of transients that Redback is designed to mainly tackle. Kilonovae, short GRB, long GRBs, supernovae, TDEs, and sort of the prompt light curve of a GRB itself. Then comes the hard part, which took a long, long time. In Redback, there's about 150 models for different transients that are directly implemented into Redback itself. And so what that means is that, for example, there's a model called RNet bolometric, which is the bolometric light curve from the RNet model for a supernova. And what that means is that for any of those models, you can basically just write a time array, an arbitrary time array, and specify a couple of parameters, and there's all documentation for that. So for example, you can say that I want the bolometric luminosity at that time array that I set, and for these particular parameters, and then as a simple Python function, you get the output of that bolometric luminosity. And it's not just restricted to luminosities. You can do magnitudes, you can do flux densities, etc. As long as the filter is defined in SVO, you can do it for that particular filter as well. And so there's inbuilt models for essentially GRB afterglows, kilonova afterglows, kilonovae, supernova, blah, blah, blah. But then they're also linking together other things that exist in other packages as well. So where possible, we are leveraging what other people have already done. So for example, there's this package called SN-Cosmo, which people use for cosmological analysis of supernovae. And so all the models in there are directly ported over in Redback, and they're just available as sort of a stream that you can reference. Similarly with Afterglow Pi, a lot of people use that to model GRB afterglows, and so similarly you can do that there. and then MOSFET, which is another package. And so that is, so basically that's the interface for calling a model. But then again, every model can be used just to show, again, for the simulation module. And so, for example, I can take one particular kilonova model, and within a few lines of code, I can simulate what that would look like exactly in ZTF or in via Rubin. And so you can already see from the top and the difference between the top and the bottom, and Rubin is not going to be that good for kilonova. And so you can do this already for ZTF and Rubin, but hopefully we can implement them for other telescopes in the near future. And again, what that enables is that you can test out your survey strategies, etc. But then because of the clean interface to Bilby, you can also do joint parameter estimation with the gravitational wave signal. So for example, if you know that there's a simulated event which was a kilonova from the same binary neutron star merger, you can link both of them, the Bilby parameter estimation on the gravitational wave side and the parameter estimation from the kilonova side to jointly infer properties. And this is, various other things you can do with that. And so this is just a couple of lines to just show the interface for fitting itself. So all the way from getting the data to actually producing a result is about 6 lines of code. So you go all the way, the first line is downloading the data. The second line is loading up that transient object. The third line is basically loading up a default prior. So for every model, there's a default prior that is loaded up. You specify a redshift or you look it up. And then you basically say, what's the settings for the sampler? So sampler in that particular case is written as ultranest, which is just a particular choice of sampler. If you don't like it, if you want to use MC, you just change that string to MC or whatever else you like. Yeah, and then you produce something like this, which is just showing the fitted of light curve. And the model in that particular case is SALT2, which is, if you like doing supernova cosmology. So I'm getting the runaround, but in case you're not converted, come chat to me. But there's already a bunch of sort of things we've done with this package already, including superluminous supernovae, tidal disruption events, GRB, afterglows, and in fact also recently taking direct outputs of numerical relativity simulations and seeing what the projected signals would look like. I'll wrap up because I've been summoned, or not summoned, whatever the right word is. If you scan this GitHub link, you will, if you scan this barcode, you will be taken to GitHub. And this is where the package is hosted. There's plenty of documentation, plenty of examples for you to get started. Awesome, thank you.